Welcome back to the Deep Dive. Today, we're plunging into a truly fascinating challenge you've brought to us. How do we genuinely build trust in, well, increasingly complex AI systems?
Yeah, it's a huge question.
You've shared a stack of sources, including this really extensive patent application, and they all seem to hint at a common thread, this relentless pursuit of precision, reliability, especially when things get super complex.
Right.
So our mission today is to unpack a groundbreaking, almost mind-bending approach to measuring trust in computational systems,
Yep.
particularly AI. We're talking about something called IntentGuard.
IntentGuard, yeah.
And it promises to transform trust from just like a subjective feeling into an objective, measurable reality.
hmm
And apparently it's rooted in the actual physics of computation.
That's what's so revolutionary here. The sources, they reveal a system that doesn't just propose a solution, but actually anchors it in fundamental mathematics and, yes, even computational physics. It's about moving beyond just sort of hoping for the best with AI and actually building an auditable, quantifiable foundation for its safety and performance.
Right, something solid.
Exactly. So what does this all mean for you, the learner, trying to navigate this rapidly evolving landscape? Let's unpack this.
Okay, so for decades, computer science has kept this really strict separation between how we think about data,
Mm.
the logical organization, and how computers actually store it in physical memory.
Yeah, that's CS 101, basically.
We've been taught this is necessary, it's foundational. But these sources suggest this very separation has, maybe ironically, created some massive headaches when it comes to trusting complex systems, especially AI.
Exactly. This seemingly fundamental separation, it leads to three core problems that consistently undermine trust in a computational systems.
Okay, what are they?
Well, first, there's translation overhead.
Yeah.
Every time a system needs to understand and find all cardiac patients over 65, it goes through multiple translation steps.
Right.
Think about it. Parsing the intent, translating it to a query, optimizing that query, then maybe multiple index lookups to find the physical data, finally reassembling results.
This sounds like a lot of steps.
It is. And each step introduces latency, it risks losing information, and ultimately, it degrades performance. It's like trying to have a critical conversation through, 5 different interpreters. Details get lost.
But it's not just slow, it's actually lossy. The fidelity drops.
Precisely. Lossy is a good word. And that lossiness, that inefficiency, it leads straight to the second problem, correlation accumulation.
Correlation
Yeah.
accumulation. Okay.
Yeah, what starts as independent categories or data points inevitably gets tangled over time. Even if you try really hard with database normalization, the reality of running a complex system means things get messy. The patent calls it denormalization and correlation buildup.
Like trying to keep socks sorted in a drawer over years.
Kind of, yeah. Imagine trying to sort 1,000 different types of item into perfect separate bins. Over months, if you're not constantly reorganizing, they start to subtly mix. This correlation accumulation, it degrades performance exponentially as the relationships get more complex, more unpredictable.
Making it harder for the system to make clear distinctions.
Exactly. And this isn't just about messy data. It actively harms the system's ability to function reliably. It's this slow, insidious degradation.
Okay, that makes sense.
And finally, the third big one, opacity.
The black box problem.
The classic black box. When an AI makes a decision, it often feels completely opaque. Because of that logical physical separation we talked about, figuring out why it did what it did means painstakingly reverse engineering through all those abstraction layers.
Which is hard, sometimes impossible.
Right. And this inherent opacity makes systems untrustworthy, unexplainable, and potentially dangerous, especially in critical areas like medicine or finance. We really need to see inside that box.
And the traditional ways we've tried to ensure AI safety, they just haven't been able to crack this, have they?
Oh.
We tried everything, right? Statistical monitoring tools that only measure symptoms, not the root causes.
Yeah, looking at the fever, not the infection.
Exactly. Or rule-based governance platforms that just can't keep up with new emergent behaviors AI comes up with.
They're too brittle.
We've even tried using AI to monitor other AI.
Which just leads to that infinite regress problem, right? The turtles all the way down. There's no ground truth, no ultimate check.
So they're trying to pull yourself up by your own bootstraps, yeah.
And even the modern tools, like vector databases, they sound promising, and they are useful for certain things.
Finding similar stuff.
Exactly. They offer meaningful proximity. They tell you similar concepts are near each other in this high-dimensional space, but they don't tell you what they actually are at a fundamental level.
You still have to search.
You still need expensive similarity searches. The address itself doesn't give you inherent meaning. They're still stuck in that old paradigm, separating the logic from the location.
Okay, so this raises a big question then. If all these widely used approaches keep falling short, what's missing? What's the key insight here?
Well, the sources suggest something pretty profound. They argue that all these previous methods lack fundamental mathematical prerequisites.
Mathematical prerequisites.
Yeah, it's like trying to navigate a really complex city with just a compass. It helps a bit, but what you really need is a detailed, dynamic map of the city itself. A map where maybe the street name is its exact physical location.
Okay, that's a cool analogy. So IntentGuard claims to have found this map.
That's the claim. It's based on 3 mathematically necessary properties that they argue any functional trust measurement system must have.
Not just nice to haves, but must haves.
Must-haves. Think of them less like clever design choices and more like the fundamental physics of AI trust, like gravity for how planets move.
Wow.
And these aren't just abstract theories either. The patent and the research notes, they really emphasize these are computationally testable design parameters. They've been rigorously validated across apparently over 1,000 real-world systems.
1,000. Okay, so they've tested this.
They've tested it. These are performance-optimized architectural choices that yield measurable advantages, both in trust accuracy and computational speed.
Okay, so what's the first pillar?
First up, orthogonal categories.
Orthogonal categories. Sounds a bit mathy, maybe intimidating.
It does sound a bit formal, but the concept is brilliant once you unpack it. In essence, it means creating measurement dimensions, ways of looking at the system that are truly independent of each other.
Independent, like
Yeah.
apples and oranges.
Exactly. Imagine trying to manage what the source material calls a semantic net of ideas. Every concept is like a cat.
Okay.
And they're all tangled up in this combinatorial explosion of overlapping relationships. A real mess.
A tangle of semantic cats. I like that.
Right. IntentGuard's job, its first job, is to herd these semantic cats.
Herd them. How do you herd semantic cats? And how do you know if they stay herded? How do you measure that independence?
You measure it very, very precisely. The sources specify a mathematical threshold for this independence. It's a correlation coefficient symbolized by rho.
Okay, right.
And this rho must stay below 0.1, none is 0, 0.02.
0.1. That seems very specific. Why that number?
It's incredibly specific because it's directly tied to how your computer's brain, its CPU cache memory, physically operates. This comes from something called cache associativity physics.
Cache associativity.
All right.
Linking semantics to hardware physics now.
Exactly. Your CPU's cache, it's designed for speed, right?
Yeah.
But it can only efficiently manage a limited number of distinct, unrelated pieces of information at once. If concepts become too correlated, if that rho value goes above, say, 0.12, your CPU literally starts to struggle.
Struggle how?
Trust accuracy plummets, potentially below 50%.
Yeah.
And critical hardware metrics like cache miss rates, they spike. You might go from a healthy 6% miss rate to over 30%.
Wow. So the computer is physically slowing down because the concepts are tangled.
Precisely. Your semantic mess becomes a physical bottleneck. So maintaining this orthogonality isn't just good data hygiene, it's a physical necessity tied to fundamental hardware limits.
That's fascinating. So how does IntentGuard maintain this?
It continuously monitors these correlations in real time. It uses specialized hardware operations, think ultra-fast parallel processing units built into the chip, like SIMD operations.
Okay.
And if needed, if correlations start creeping up, it automatically applies mathematical transformations like Gram-Schmidt orthogonalization to restore independence. And it does this within milliseconds.
So it's constantly self-correcting, keeping the cats herded.
Exactly. Active, ongoing maintenance. And this ensures that measuring one category doesn't mess with the measurement of another. You get true isolation of where problems or drift might be coming from. And that enables the next crucial pillar.
Okay, what's pillar number 2?
Pillar 2 is unity architecture.
Unity architecture.
And this tackles that fundamental translation bottleneck we talked about earlier, that constant, inefficient back and forth between the logical meaning of data and its physical storage location.
Right, the separation that computer science has taught for 50 years.
Exactly. This unity concept is a huge departure from that orthodoxy. It basically throws out the rulebook that says you must separate logical and physical layers for data independence.
Okay, so what does it propose instead?
The unity principle states, Semantic structure, a physical memory layout, hardware access pattern.
Structure equals layout equals access pattern.
Yeah. Think of it like
Yeah.
realizing electricity and magnetism weren't separate, but two sides of the same coin,
Right.
electromagnetism. Here, the semantic path is the physical memory address.
Whoa. Okay.
The sources call this achieving meaningful identity, not just the meaningful proximity you get with vector databases.
So give me an example. If I wanted to access, say, health.cardiac.heartrate,
Hmm.
how does that work differently here? And what are the engineering challenges? Because this sounds radically different.
It is radical. So traditionally, the system parses that path, health.cardiac.heartrate, then does multiple lookups through indexes, maybe B trees, pointer chasing, to finally find the physical data blocks.
Right, the multi-step translation.
With Unity architecture, it's different. A deterministic hash function, something fast and reliable, like CRC32C using hardware acceleration, directly computes the physical memory address from that semantic path string itself.
So the path health.cardiac.heartrate always maps to one specific address, like 0x110B00C0.
Always. Directly computed. No complex tree traversals, no multiple lookups bouncing around memory.
No lookups, no translations, just direct access. That sounds almost too good to be true given how we've always built databases.
It does go against the grain, doesn't it? The challenge, the engineering feat, was finding a way to make that direct mapping totally deterministic, collision-resistant enough, and super performant.
But they claim they did it.
They claim they did. And the result is constant, immediate access time. We're talking O1 access, verified by directly counting hardware clock cycles with apparently less than 5% timing variance.
Constant time. O1. That's the holy grail for access speed.
It pretty much is. It eliminates those huge overheads of traditional lookups, saving hundreds, maybe thousands of CPU cycles per access.
And that's the key difference from vector databases then. They cluster similar things, but you still have to search the cluster.
Exactly. Vector DBs give you proximity that these things are kind of like that thing. IntentGuard aims for identity. This name is this exact spot. The address is the complete hierarchical meaning. You don't search for the book. Its title is its precise coordinates on the shelf.
Okay, mine's slightly blown. Orthogonal categories, Unity architecture. What's the third piece?
The final piece of the puzzle is multiplicative composition.
Multiplicative composition.
Yeah.
How does that fit in with this orthogonal unified space?
This is where the real magic happens, leading to those dramatic performance gains mentioned in the sources. See, in traditional systems where everything's correlated and tangled, individual improvements or failures tend to just add up. You fix one part, the whole system gets a bit better. One part fails, the system gets a bit worse.
Linear of X.
Pretty much linear, yeah. But when your categories are truly orthogonal, properly independent, like we discussed, their effects multiply.
Multiply. So instead of performance plus P,
Yep.
it's performance POP.
Exactly.
It's a massive difference.
Yeah, exponential
A
again.
massive exponential difference. It reminds me of system safety engineering, like in aerospace.
Yeah.
A single critical component failure doesn't just degrade performance slightly. It can cause a cascading catastrophic failure. Even if 99% of the system is fine, multiplicative effects capture that risk.
Right. So this isn't just about boosting performance. It's about correctly modeling risk, too.
Absolutely. You've got it. It's an exponential leap, and they say it's empirically verified. The sources mention validation across 47 documented failure scenarios where this multiplicative composition correctly identified emergent system failures, where the whole system goes down because one critical part failed.
Precisely. The overall trust score approaches 0 if any critical category fails badly. Additive models, on the other hand, they often generate this false confidence. They average things out, masking a critical weakness until, boom, it's too late.
But hang on, if one category truly goes to 0, wouldn't that multiplication instantly make the whole system's trust score 0, even if other parts are okay?
That's a critical point, and the patent apparently addresses it directly. The refined model for TU, that's the trust score for an individual category, uses a small non-zero value called epsilon.
Epsilon, like in calculus.
Exactly like that. It means a category's score can get infinitesimally small, incredibly close to 0, but never absolute 0.
Oh, okay.
This mathematically captures that idea of a single failure point causing a near-total collapse in trust or function, without literally making every single number 0. It creates a powerful forcing function for alignment, basically. Strong pressure to keep all critical components healthy.
Makes sense. And this multiplication, is it computationally expensive?
Apparently not as much as you'd think. It's hardware accelerated, leveraging things like logarithmic multiplication using the FPU, the floating point unit in the CPU. This helps achieve those reported 100x to 1000x performance improvements.
Okay, so these three pillars, orthogonal categories, unity architecture, multiplicative composition, they work together
Convergently, yeah.
to allow IntentGuard to quantify something that was previously, well, unmeasurable. Trust debt.
Trust debt, that's the core metric.
So what exactly is trust debt? Laid out for us.
Okay, so trust debt is defined as the exponential accumulation of drift between a system's intended behavior and its actual observed reality.
Drift, like the system slowly drifting away from what it was supposed to do.
Exactly. But let's break down the idea before the math. It's essentially the accumulated difference between intent, what you want it to do, and reality, what it actually does, observed in that independent orthogonal space we talked about.
Okay, the difference.
Then that difference gets compounded. Factors like time passing, how old the original specs are, the importance or weight of different categories, they all multiply the debt.
So older systems, or more critical parts drifting, accrue debt faster.
Precisely. And finally, it's all multiplied by the overall health of all the categories involved, that multiplicative composition, CE. The full formula looks like U x S x day.
Right, okay. That integral form looks complex, but the core idea, if I'm a CTO trying to manage my AI systems, this one number, this trust debt score, it basically tells me how much mess or drift has built up, how much my system is struggling.
That's a great way to put it. How much quality of struggle is happening? How hard is the system physically working just to keep its head above water, to stay aligned with its intent?
And you said physically working.
Yes. And this is the truly groundbreaking part, according to the sources. Trust debt doesn't just exist as some abstract mathematical concept on a dashboard. It manifests as measurable hardware phenomena, literally impacting the physical chip's performance. We can see and measure this using specific hardware performance counters directly from the CPU's own monitoring capabilities.
Wait, hold on. You're saying semantic misalignment, the concepts drifting apart, has a direct physical impact on the silicon chip. That we can measure.
That's exactly what they're claiming. It's incredible, right?
Yeah. How do you measure?
For example, they track L2 cache misses. When semantic drift causes random, unpredictable memory access patterns because the concepts are tangled, your CPU's L2 cache just can't find the data it needs efficiently. Cache misses go up, measurably.
Okay.
Then there are branch mispredictions. Tangled logic, unpredictable data flows mean the CPU guesses its next instruction poorly more often, more mispredictions, more wasted cycles, again, measurable.
Right.
And finally, pipeline stalls. Unexpected data dependencies, which are a hallmark of systems drifting out of alignment, cause the CPU's internal processing pipeline to just grind to a halt, waiting for data it can't find quickly. More stalls. Measurable.
So low trust debt translates directly to predictable memory access, accurate branch prediction, smooth pipeline flow, basically an efficient, happy chip.
Exactly.
And high trust debt means your computer is literally struggling physically because the AI's understanding has drifted from its original purpose. It's like a real-time EKG for semantic health.
You've absolutely got it. They're arguing that semantic misalignment is a physical phenomenon, not just an abstract software problem. And this provides an objective, auditable measurement, transforming trust from gut feeling to actual computation.
This sounds incredibly powerful in theory, but the big question, does it actually work in the real world? What's the validation?
That's always the key question, isn't it? According to the sources, yes, IntentGuard has been empirically validated across over 1,000 code repositories. They achieved an average orthogonality, that row value, of 0.09, right in that target zone below 0.1.
Impressive consistency.
And interestingly, they ran the system's own diagnostic, called Grade C, on its own unfinished code base.
Eating their own dog food, huh?
Exactly, and it found 4,423 units of real trust debt. This apparently proved the measurement works on actual, messy, in-progress semantic misalignment, not just clean theoretical examples.
And what about that asymmetry ratio mentioned, 3.51x?
Right, the 3.51x asymmetry ratio. That revealed they were building significantly more code and features than they were documenting or defining in terms of intent, which is exactly what you'd expect from a research-heavy, rapidly evolving project. The reality vector was outpacing the intent vector.
Okay, so the measurement itself seems validated.
Yeah.
What about the impact of achieving this low trust debt state? Those performance numbers look pretty wild.
They are staggering, aren't they? The sources highlight these performance improvements. A 361x speed up in a medical diagnosis application.
361 times faster.
Yeah. a 95x improvement in financial risk assessment speed, 40x latency reduction in brain-computer interfaces. That's huge for real-time control.
Wow.
And maybe the most dramatic, a 3,750x speed up in a complex supply chain optimization problem.
3,700. These aren't just tweaks. These are fundamental shifts in what's possible.
That's exactly how the sources frame it. These aren't just incremental gains. They reflect a fundamental phase transition in the underlying physics of the computation.
A phase transition.
Yeah, by enforcing orthogonality and unity, the system moves from an additive, somewhat chaotic state to a multiplicative, highly ordered, highly efficient state. It unleashes exponential performance. It's playing a completely different game, like going from, I don't know, walking to flying.
This clearly isn't just about AI safety then, is it? It's a massive competitive advantage.
Huge.
You brought up the finance use case earlier. I can see it now. Imagine a hedge fund currently using some opaque AI for trading.
Right. A black box making bets.
If they could suddenly use something like IntentGuard to visualize the why behind the AI's decisions, see those hidden correlations, measure and reduce that semantic drift, they'd gain what the sources call informed confidence.
Informed confidence. I like that.
It means they could potentially make bigger, more strategic bets because they actually understand and trust their system's reasoning.
Yeah.
Maximize wins, minimize those catastrophic hidden losses. It could be like, well, the impact the Black-Scholes model had back in '73 for options pricing.
More like Renaissance technologies, right? Becoming legendary through fundamentally superior math and a deep understanding of their algorithms, not just faster execution. This could be that next kind of leap.
Absolutely.
And the strategic implications, they go way beyond just performance gains. Think about regulation, the EU AI Act, for instance.
Right, that's coming fast.
It's mandating explainable AI decisions, measurable safety metrics, with huge fines, up to 35 million or 7% of global revenue for noncompliance.
Ouch.
IntentGuard, by providing these exact hardware-grounded, auditable measurements, seems tailor-made for that kind of compliance need. It potentially transforms AI liability from this unlimited, terrifying unknown into manageable, measurable risk.
Which could unlock other things.
Well, the sources suggest it enables a massive potential market, a $2.7 trillion AI insurance market. Because if you can finally quantify the risk of an AI system going wrong, you can actually insure it.
Wow. You can't insure what you can't measure.
Exactly. This provides the measurement.
And crucially, the source also mentioned this creates a patent moat. Why is that?
Because the claim isn't just, here's a way to measure trust. The claim is, here are the mathematical and physical requirements any working system must have.
Claiming the fundamentals.
Right, validated mathematically and empirically. And it fundamentally goes against 50 years of industry teaching away from unifying logical and physical layers. That makes it inherently disruptive and potentially hard for others to replicate without infringing or rethinking everything from the ground up.
So wrapping this up then, what we've really discovered in this deep dive is, well, it feels like a revolutionary approach to understanding and managing AI.
It really does.
IntentGuard isn't just giving you a better company to navigate AI complexity. It's giving you a whole new map. A map where the territory and the map are unified.
That's a great way to put it.
It quantifies the unmeasurable trust, alignment, drift by rooting it all in the observable physics of hardware performance, giving you unprecedented visibility and control.
And we've seen how those three pillars, orthogonal categories, unity architecture, and multiplicative composition, aren't just clever ideas. They're presented as the mathematical prerequisites, the necessary conditions, for transforming AI trust from that subjective guess into an objective, auditable reality.
A system that lets you finally manage that semantic net of cats with real precision. Keep them in their lanes.
Keep them herded, yeah. Ensure they don't tangle things up.
It sounds like a tool that lets you see the exact quality of your project's journey, its struggle, towards that ideal state of perfect alignment, where the physics of trust are understood and actually harnessed, making your systems perform not just incrementally better, but maybe fundamentally smarter and safer.
I think what really stands out from this deep dive for you, the listener, is this idea that AI might be about to undergo a profound phase transition. We could be moving from systems where trust is an unmeasurable hope, a guess, to systems where trust is a quantifiable physical phenomenon. So the final question, the provocative thought perhaps, is this. Are you ready to navigate this new physics? Are you prepared to build and deploy AI with this kind of true, verifiable confidence? Or will you be left behind trying to map this entirely new world with an old, outdated compass?